Hi, I'm Professor Stugart, and today I want to talk about one of the most common mistakes that almost everybody tends to make when it comes to dealing with statistics, and a particular problem that shows up when we're talking about percentages. And in fact, this problem happens so often and can have such weird consequences that there's actually a special name for it called Simpson's paradox. And so I want to take a look at Simpson's paradox today by going through one of our worksheets that you should find attached to your email. And we're going to kind of talk about it and go through an actual example to see why these mistakes show up and how easy it is to make them. So you have your worksheet in front of you. The instructions say we have a patient who's diagnosed with cancer and is given two options for treatment. Treatment A and treatment B both have been tested on patients for the last 3 years. The results of each trial year are given below, and well, in this case, I'm going to show you in just a second on the screen. And what we want to do is find the percentage of patients that were cured for each trial year. Then we're going to add up each of the trials over the 3 years. And once we add up the 3 years, we're going to look at what were the overall percentages of people getting better. So what we should do now is, let's take a look at the data. So here's the data, and we have treatment A and treatment B, and we can see that we have the years 2018, 2019, and 2020. So if I want to find out what percentage of the patients were cured in each one of those years for each one of those treatments, I'm going to go through one by one and, well, use my calculator. So for the first one, there were 12 patients cured out of the 48, which means I'm going to divide. I'm going to do 12 divided by 48 on my calculator, find my answer, and remember, when I do that division problem, that's giving me my proportion. That's not a percentage yet. If I want to turn it into a percent, I have to multiply it times 100. And so I multiply it times 100, and that gives me a percentage of, well, 25%. 25% of people were cured using treatment A in the year 2018. All right, now let's do the same thing for treatment B in the year 2018. Same idea. In this case, we're doing 104 divided by 411. And hopefully you're doing this along with me, right? Everyone has their calculators out and their pencils and the paper, and you're doing this too, right? If you need to pause the video, take your time to pause the video because you should be doing this yourself. Obviously, doing any sort of math involves writing things down, right? And using your calculator. If you don't get practice pushing the buttons, even for simple things like this, you're going to be more likely to make those mistakes when it comes to times when you're doing exams. And let's not do that. Let's get all those mistakes out of our systems before exams start. So anyway, I divide those two numbers, and again, if I want to turn it into a percentage, times it by 100, so it looks like that percentage is 25.3 if I round to 1 decimal place. All right, so now let's do that. Well, now we have our two percentages. Let's compare. So which one was better? Well, it wasn't by a ton, but in this case, it definitely looks like treatment B worked better in 2018. You would have had a higher percentage chance of being cured if you were in treatment B's group. All right, now let's take a look at 2019. So same idea as before. I'm now looking at treatment A. So let's see, 183 people were cured divided by the 582 people. I get my decimal answer, and I multiply it by 100. There we go. And so it looks like 31.4% when I round it to my 1 decimal place. Okay, so let me move myself over a little bit so that we can see the whole table with all of our data points. And now it's time to do treatment B for 2019. So 45 divided by 140, take that result, multiply it by 100, and that's a pretty good one there, isn't it? 32.1%. So 31.2% in our table. And again, let's compare. So which one was better? So treatment A was 31.4%. Treatment B was 32.1%. So again, it looks like absolutely treatment B was the better choice in 2019. If you wanted to have your cancer cured, you would have had more luck if you were in treatment B's group. All right. So hopefully we get the process. So I'll go a little bit quicker now. And I'm actually going to let you do the year 2020 on your own. So do the year 2020 on your own. Pause the video if you need to take a few seconds. I'm about to keep going. And I'll tell you that for treatment A, the percentage of people cured was 29.1%. And again, pause the video. Wait a second. Do 2020. Divide those two numbers, multiply by 100, and 32.9%. All right, this one doesn't even take much looking at. It seems pretty clear to me that, again, in the year 2020, treatment B was definitely the better option. And good. So that means in 2018, in 2019, and in 2020, every single time, treatment B was the better option. So it seems pretty obvious that treatment B is the best plan, right? That if you have this choice, you're this patient, and you're like, well, would you rather be in treatment A or would you rather take treatment B? It seems like treatment B is definitely the better option, but let's make sure that that's actually the case, because we should actually look at the 3-year totals here. And so I'm taking a look at these 3-year totals. Well, I got to add up each column. So if I add up the number of people cured from treatment A, so that's going to be 12 plus 183 plus 190. So again, that looks like I'm getting 385 for that particular one. And add up the other ones. And again, let's see, if I do 48 plus 582 plus 654, that's going to be 1284. And again, please tell me you're still following along and adding the numbers on your calculator. It's about as easy as it's going to get in this class. So let's hope we're doing it. All right, and then the last step, of course, for treatment A, divide those two numbers. So 385 divided by 1284, times that by 100, and I get, 30%. When I round it to one decimal, it rounds up to exactly 30%. Okay, so that means over the 3 years, you would have had a 30% chance of being cured if you chose treatment A. Now let's do the same thing for treatment B. So add up all the people that were cured. So 104 plus 45 plus 163. That gives me 312 people who are cured. And we'll add up the total number of patients. 411 plus 140 plus 495. That's 1,046. And so now all we have to do is divide those two numbers, times it by 100. Again, follow along on your calculator. And we get 29.8 when I round it. 29.8, which means over the 3 years, wait a second, treatment A was better? Treatment A worked better over the 3-year period? So in each one of the individual years, you would have been better off with treatment B, but overall, over the entire 3-year trial, treatment A actually ended up working out better? Wait. That doesn't make a lot of sense. Well, that's why it's called the paradox, because when you look at this, you're like, wait a second, none of this makes sense, because my intuition for percentages is that I should be able to just compare them like this. They should just work really nice and neatly, except that's not the case, because percentages aren't really what you think they are. We talk about percentages, and we have that word percent at the end, that it sounds like it's a unit. It sounds like the same thing when we're talking about minutes or hours or miles or gallons or any other sort of unit where, again, we can compare them directly. As long as I'm talking about miles, well, if it's 120 miles to Boston, but only 90 miles to New York, clearly New York is closer, right? Boston's further away because I can compare them because they have the same units. Percentages are not units. That's the key here. Percentages are not units at all. Percentages are actually just kind of an interesting notation. So what is actually going on here? And I'm going to talk about percentages a little bit more in just a second, but what is going on here? Why would this happen? Why can I not compare my percentages the way I intuitively think I should be able to? When I look at this table, I feel like I should be able to compare them, but I can't. And why not? Well, the key is that each time I found these individual percentages, well, the way I found them is my first step was to divide. Because what's really going on here is that these percentages are really fractions. I was really dividing. I have a numerator, the number of people cured. My denominator is the total patients that were given that treatment, which means what I'm dealing with is actually a fraction. If I want to be able to compare fractions, if I want to be able to add and subtract fractions, I need a common denominator. And in none of these columns did I have a common denominator. My denominator were the number of patients. So my denominator was 48 and 582 and 654 and 1284. None of those had the same denominator, which means I cannot compare them because they're not going to end up, well, with the same basic size. Percentages don't work that way. And so you ask yourself, that doesn't make any sense. I hear these percentages and people throw out percentages all over the place, all over the time. People are always comparing them. Is everybody idiots? Well, no. They're probably just trying to push their own agenda. And that's why it's important that you understand what these things are. Because everybody in this world is going to be out for themselves. All right? And if they benefit from you being misled, well, then they're going to do that. It's not that they're out to get you. Very few people in this world are actually out to get you. But they are out for themselves. And because they know more than you, they'll take advantage of that fact, which is why we need to learn as much as we possibly can. And percentages are a really, really good way to take advantage of people. Now, the nice part is the word percent actually tells you exactly what's going on in the word itself. The word percent, well, if we split it up into its two parts, the word per, and again, we've heard the word per probably a lot. We talk miles per hour. We talk miles per gallon. We use that word a lot. And again, if you're trying to calculate the mileage that your car gets, the miles per gallon, your fuel efficiency, you take the number of miles you drove and divide it by the number of gallons of gas you used, miles per gallon. And you set it up as a fraction, which means the word per just means divide by. That's all the word per means, divide by. And then the word cent. Well, we've heard the word cent before, right? How many cents are in a dollar? How many years are in a century? If you're speaking Spanish, what does ciento mean? Or even Italian, I think, sounds about the same. Well, it all means 100. So the word percent literally just means to divide by 100. And in fact, you can actually see this when we look at the symbol for percent. That percent symbol, whenever you see it, literally just means take that number and divide it by 100. That's the real value that you're looking at. And in fact, when we did the multiplication, right, we were doing these problems on our calculator, I times everything by 100 to turn it into a percent, which means I was actually doing that process anyway to make my percent. And that symbol demonstrates the fact that I multiplied by 100. So if you want to get back to the real value, you better divide by 100. And so be really careful. Anytime someone compares percentages, or in particular, if they start subtracting percentages, if they tell you, oh, the percentage of voters that did this subtracted from the percentage of voters that did that, they're lying to you. That is absolutely being manipulated unless they're talking about the exact same size population of voters, which would be impossible because if you subtract from the same number, then, well, that really doesn't make a lot of sense, does it? Anyway, hopefully this helped explain one of the ways that people are easily misled by statistics, and hopefully it's something that you're not going to fall for again. So everybody take care. Good luck learning statistics.